And welcome everyone to the second part of our 20-second lecture in our probability and statistics course. So today we are going to shift the focus. In the first part of today's lecture, we thought about having an acceptance region handed to us and us finding the associated significance level, the value of alpha, the probability of a type 1 error. So if somebody just handed us a statistical test, we would be interested in finding the probability of a type 1 error for that test as sort of a way of us thinking about, how good is this test or what is the nature of this test. More realistic, as we have said, is the process of deciding what alpha should be ahead of time and then using that value of alpha to determine what the critical values for your test are. Once you have the critical values, you have the acceptance region, you have the critical region. That's the realistic scenario. So here's an example of how that kind of a scenario might play out. Suppose you work for the Ministry of Health for some country, and we are going to assume that this is a utopian country where there is just an abundance of resources provided for public health. So a lot of the tax dollars that are collected in this country are used to make sure that the citizens of this country have access to quality medical care and that they have all the resources that they need. And doesn't that sound lovely about this time, this being April of the year 2020 when this lecture is recorded? So suppose you work for this Ministry of Health, whatever it may be, something like our Department of Public Health. Suppose also that there is a disease that is endemic in the population at this point and a new vaccine has been developed. We could think about SARS-CoV-2 here, as we are currently experiencing a global pandemic, which those of us here at SUNY New Paltz are pretty dang close to the global epicenter of. So, suppose some new vaccine has been developed for SARS-CoV-2, and we are statisticians working in the Ministry of Health, and we have to decide whether or not to deploy this vaccine. So maybe there's a rush to deploy because the population is experiencing a pandemic in the way that we are currently. And so some preliminary testing has been done, but we don't have the amount of testing that we would like. The vaccines that we use regularly, things like the annual flu vaccine or the MMR vaccine, or some of the other vaccines like the tetanus vaccine that people get regularly, those have been extremely well tested. So those have been vetted for years. There's just a wealth of data, and we understand the risks, the little risks that exist for those vaccines. So those are very well understood. A new vaccine that's being developed in a rush in response to a current and ongoing outbreak, that's not going to have the same wealth of testing that's been done for it. So we have some level of testing for this new SARS-CoV-2 vaccine, this new coronavirus vaccine, but we don't have as much as we would like. Let's say that mu is going to be a population parameter associated with this new vaccine, and mu is going to be the average resistance factor conveyed by this vaccine. And this can get a little bit complicated. The upshot of what I'm saying is that we will save lives. This vaccine will save lives if mu is greater than 1, and it's not actually going to help if mu is less than or equal to 1. So mu is like the degree to which it increases your resistance. Mu equal to 1 would mean your resistance stays exactly the same. We're going to say that mu less than 1 doesn't. It also means your resistance stays exactly the same for this vaccine. But mu greater than 1 means you gain some resistance. You become more resistant to infection by this virus if mu is greater than 1. So if mu is actually greater than 1 and we deploy the vaccine, we will save lives. If mu is less than or equal to 1 and we deploy the vaccine, we're not going to help things actually, but we're not going to hurt anyone. The vaccine is safe for humans. It's just not helpful in the case that mu is less than or equal to 1. So our early trials seem to indicate that mu is greater than 1, but we're going to test that at least a little bit further, and we have to decide what kind of statistical tests that we want to do now. What is an acceptable level of significance for this further testing based on the real-world consequences of the different types of errors? So we have reason to believe mu is greater than 1 based on some very early trials, and that's our null hypothesis. The null hypothesis states that mu is greater than 1. The alternative hypothesis then would be that mu is less than or equal to 1. This is a one-sided alternative hypothesis, and really a one-sided null hypothesis as well in some sense. So we have not been thinking about hypotheses of this type in our class to this point, and we're not going to deal with them in a quantitative way. So I might state one-sided null and alternative hypotheses of this type just for us to explore these ideas of the different types of errors involved. But we're not going to have to do any kind of quantitative calculation for scenarios of this type. They're real and they exist. They're just, we don't have time to discuss them in detail. So we're only going to make use of them in the context that we are currently in, which is discussing the choice of a significance level based on the real-world ramifications of the different types of errors. So, in this setup, we have to decide we're going to, again, run another test here to determine whether or not we believe this null hypothesis, and we have to decide on an acceptable level of significance for our test. So we want to think about what does a real-world type 1 error look like. In this scenario, what does a type 1 error mean in real-world terms? And what does a type 2 error mean in real-world terms? So what does a type 1 error look like here? A type 1 error occurs when the null hypothesis is actually true, but your testing leads you to reject it. So here, if the null hypothesis is true, that means our vaccine works. That means that the deployment of this vaccine could actually save lives. If our testing results in us rejecting that hypothesis, that means we don't believe that the vaccine works, even though it does, and we fail to deploy what would have been a life-saving vaccine. So this is a case that results in preventable deaths. If we make a type 1 error here, we will have had a good and working vaccine on hand, and we will have failed to deploy it because our statistical test of hypothesis led us to believe that it was not an effective vaccine. And this is generally the worst case scenario for public health workers. Preventable deaths, that is what we are working exactly to prevent, right? We're working to prevent the unnecessary loss of life in any way that we can. So this is sort of the nightmare scenario in a type 1 error here. What does a type 2 error look like? Type 2 errors occur when the null hypothesis is actually false, but your testing leads you to accept it. So here, our vaccine was actually useless. It wasn't going to help anybody. The null hypothesis was false, so mu was actually less than or equal to 1. But our testing led us to believe that it was an effective vaccine, and we deployed it. In this way, we wasted our time and we wasted our money actually deploying this vaccine. We didn't kill anybody. We didn't hurt anybody. But it wasn't any better than just not having a vaccine to begin with. So we have the two types of errors: preventable deaths resulting from type 1 error, and a waste of time and money resulting from a type 2 error. We're going to return to this type 2 error in a moment, but let's say that these are the consequences for now of the two types of error. If that is the case, then we see a type 1 error is worse here. We want to minimize the chance of a type 1 error, so we would want a smaller value of alpha, even at the cost of a larger beta. If we have to make a trade-off between alpha and beta, we want alpha to be smaller, even if beta is larger, because we have deemed a type 1 error to be much worse than a type 2 error here. Let me back up a moment and say, you can make secondary arguments about what the consequences of a type 2 error are here as well. So realistically, if you think you have a vaccine that's going to work, but it actually doesn't, that might cause you to stop looking for other vaccines. And so the search for actually effective vaccines could be delayed, and that also results in preventable deaths. It's also possible that you're wasting the time of your healthcare workers who are going out and administering an ineffective vaccine, I should say, and that is going to cause an increase in the mortality rate because we need those healthcare workers deployed in other sectors. It's, as we said here, this is a fantasy scenario where we have plenty of healthcare workers. They all have plenty of money. There's abundance of resources being poured into this problem, which sure sounds nice. But there are arguments to be made as to how a type 2 error could result in sort of some secondary effects, like if we're spending our time on this and we're not spending our time on other things that would be more effective, that would result in preventable deaths. Those are absolutely real arguments. I'm oversimplifying things here in a small way, just to try to illustrate a situation which is more clear-cut than situations actually are in the real world for the most part. So there's not one right answer, and if you were to argue effectively, you could make cases other than the one that I've given here that would receive full credit if a question were asked on this type of a topic. So just in case you were thinking about some other consequences of creating or making a type 2 error here, I agree that there are other more serious consequences that you could consider as sort of secondary effects, in the sense that they're not primary, like, prevent somebody not receiving a vaccine that would have saved them directly causes their death. Here it would be more about if you're spending your time on something that's ineffective because you believe it's effective, that's taking resources away from the search or the employment of more effective techniques, either the search for or the employment of more effective techniques. So it's a fair point. But if we assume that those are the consequences, the ones that I've given are the consequences of a type 1 and a type 2 error, type 1 errors are worse, and we want a small alpha even if it means a large beta. At this point, we'll state that a value of alpha that is very, very commonly used is alpha equal to 0.05. So this has been the standard for a long time throughout statistics. When I say the industry standard, I mean the industry of statistics. So across all sorts of practical industries and scientific endeavors and public health epidemiological type surveys, an alpha value equal to 0.05, a significance level of 5%, is the norm. That is what people tend to use by default. And actually, in the last decade or so, there's been some pushback against that, and folks are starting to recognize that it doesn't make a lot of sense to just knee-jerk to the same value of alpha all the time, but instead to think about consequences in the way that we're doing in this example. So tailor your value of alpha to the actual impact that a type 1 versus a type 2 error would have in the real world here. So it's starting to become slightly less common that people always use alpha equal to 0.05, and we are certainly going to think about how we might want to change our alpha values from that for certain situations. We will take alpha equal to 0.05 to sort of be the standard value, and so in the example that we considered here, where we see that a type 1 error is much worse for us than a type 2 error, we want to lower the value of alpha. We want to accept less risk of a type 1 error occurring relative to the standard level of risk that's considered acceptable, 5%. So maybe we take alpha to be 1% instead of 5% because we want to have less of a chance of seeing a preventable loss of life, even if it means increasing the likelihood of some unnecessary expenditure on an unworking vaccine. It occurs to me that this is somewhat analogous to Bill Gates building 7 factories for the 7 most promising coronavirus vaccines, knowing that probably 6 of those 7 factories, certainly 5 of those 7 factories, aren't going to be useful. So he's accepting a loss of money for the sake of a quicker deployment of the vaccine. Don't tell the conspiracy theorists that I said that Bill Gates deployed the virus. Alright, so that's the idea here. You got to think about, what does a type 1 error really mean? What does a type 2 error really mean, which is worse? And do I want a smaller alpha because I think a type 1 is worse? Or would I take a larger value of alpha, resulting in a smaller beta, because I think a type 2 error is worse? So in the above example, if we had decided that a type 2 error was the bad kind of error, the worst type of error to make, then maybe we would have gone for a larger value of alpha relative to the 0.05 standard value so that we could decrease beta by making alpha larger, as we discussed in the first part of today's lecture. So that is the idea. We'll see some of these in homeworks. We'll probably have some of these on our final exam where we think about a real world situation and we have to decide which type of error do we think is worse and what does that mean for our choice of alpha. Now we're going to take a choice of alpha and we're going to use that to find the acceptance region for our statistical test of hypothesis. So we're going back to our building a vertical lift rocket example where a manufacturer is claiming that the average mass of their components is 50 grams. We know the standard deviation to be 2.5 grams. We're going to take the test statistic to be a sample mean for a sample of size 40. And instead of somebody who doesn't know anything about statistics handing us an acceptance region for that test statistic, Instead, we, who know something about statistics, are allowed to design the experiment, and we decide that we'll stick with the industry standard value of alpha 0.05. So we decide that this is a fairly standard level of risk for type 1 versus type 2, and we're going to take an alpha value equal to 0.05. We now want to find the acceptance region. So this is before we make any observations. We're still sitting at our desk with pen and paper designing this experiment. We know that we have the budget to buy 40 of these components, and we've decided that we'll accept a 5% risk of a type 1 error, and we are now going to calculate what are those values for our test statistic that will be considered acceptable and will result in us believing the null hypothesis, and equivalently, what are those values for our test statistic that will be considered unacceptable and will result in us rejecting the null hypothesis that mu is 50. So ultimately, the way to find the acceptance region is to recognize that we're going to be computing this sample mean, x sub 40 hat, and we're going to use the central limit theorem to write that sample mean or we're going to rewrite that sample mean in this way, so that the central limit theorem will tell us that this expression is approximately the standard normal z. So this is what we're going to find. We're actually going to get 40 of these components, mass them, and find the sample mean. We're going to modify that into an expression of this type, because this expression is approximately a standard normal. The idea is that if x sub 40 hat is close to 50, that happens exactly when z is close to 0. We've seen lots of examples where when you standardize, you maintain the same type of problem. So saying that your normal random variable is close to its mean, and then you standardize, and it becomes equivalent to a problem where z is close to 0, z's mean. And so that's the idea. So we're going to believe these folks if our sample mean turns out to be close to 50. Once we take this procedure and once we perform this procedure, calculate this expression, we make our approximation that expression is approximately standard normal, then that event, that sample mean is close to 50, becomes the event that z is close to 0. So we are going to believe the sample mean if this expression, which is approximately z, is near 0, and we're going to reject the null hypothesis if that expression that we observe and then calculate is far from 0. We observe x sub 40 hat, and we calculate this ratio. If that turns out to be far away from 0, then we don't believe that the mean was truly 50. If this turns out to be close to 0, then we do believe that the population mean was actually 50. So again, the idea here is that, and then our 5% acceptance rate, our 5% significance level rather, that is the chance to reject H0 if H0 is true. And so when we say that we will accept a 5% chance to reject the null hypothesis when the null hypothesis is true, that translates to us accepting a 5% chance for this to be far away from 0. If the null hypothesis is true, then this is approximately z. And so we're saying that there should be a 5% chance that this ends up being far away from 0, quote unquote. And it's this 5% chance that's going to determine what far away from 0 actually means. So this is a fairly important bit of conceptual work that we're doing here. This idea that when we decide on our significance level that there should be a 5% chance to reject the null hypothesis when the null hypothesis is true, that means that we're accepting a 5% chance that the null hypothesis is true, so this really is approximately a standard normal, but it still ends up being far away from 0. And that determines what we mean by far away from 0. We're ultimately looking for this as z0 and z1, so that a standard normal, z, has only a 5% chance of ending up in this left tail or ending up in this right tail. So further from 0 to the left than z0, and further from 0 to the right than z1. And so we want the sum of the areas of these tails to be 5%, meaning each of the tails has the area 0.025. We want a z0 and a z1, and we want symmetry in it because there's symmetry built into the standard normal density function. So z0 should be the opposite of z1, such that the area of the left-hand tail is half of that 5%, and the area of the right-hand tail is likewise half of that 5%. So a 5% chance that a standard normal shows up far away from 0, where far away is given by Z0 and Z1. Our chart for phi, if we look for that 0.05/2 value and we try to find the input to phi that'll give us that output, we get our famous 1.96 back. So Z0 is going to be negative 1.96 and Z1 is going to be 1.96. As we're going to see, there's a lot of overlap between what we're doing here and what we did for confidence intervals, because the mathematics of both of those scenarios is based on the central limit theorem. So we are now saying that we are going to reject the null hypothesis if this quantity turns out to be less than a negative 1.96, or if it turns out to be greater than positive 1.96. Which is to say, we are going to accept the null hypothesis if this quantity falls between negative 1.96 and 1.96. This is an interval for this elaborate expression, which is approximately z. We can translate that into an interval for x hat sub 40 itself by simply multiplying this denominator over to both sides and adding 50 to both sides, and we get our acceptance region for our test statistic. We now are going to accept the test statistic if it falls between this number and that number, and we will reject it otherwise. So we have our acceptance region. Our acceptance region looks like this. The critical region would be everything but, so from negative infinity up to this point, union with this point out to negative infinity. And our critical points are, our critical values are exactly the left and the right hand boundaries here for the test statistic. So we knew that we wanted to accept the null hypothesis if x sub 40 hat ended up close to 50, and this gives us an interval centered on 50 such that if you assume the null hypothesis is true, there is only a 5% chance that our test statistic falls outside of this interval. That is, a 5% chance to reject the null hypothesis under the assumption that the null hypothesis is true. Excuse me. So, summarizing our findings here, this is the theorem that's going to give us the acceptance region for a significance level of alpha. For a statistical test of hypothesis using sample mean as the test statistic, where the null hypothesis asserts a value for population mean. So if you have a population, your variance is known, the central limit theorem applies, so variance is finite and it is greater than 30. N is greater than 30, your sample size. And if your null hypothesis asserts a value for population mean, whereas your alternative hypothesis is the two-sided alternative hypothesis that population mean is simply not equal to that value, then the acceptance region for your test statistic, sample mean, for a statistical test of this null hypothesis with significance level alpha is given by this formula. The acceptance region is this interval, mu naught minus z sub alpha over 2, sigma over root n, and then mu naught plus that same expression. And here, as before, z sub alpha over 2 is a number such that phi of the opposite of that number gives you alpha over 2. You have to take alpha over 2 to be the output of phi and find the appropriate input that gives you that output. So again, the big picture is that you decide alpha based on real-world considerations of the ramifications of a type 1 versus type 2 error. Once you've decided what level of likelihood of a type 1 error is acceptable, that dictates your critical values. That dictates what your acceptance region looks like. And you compute it using the methods that we've done here, including this final theorem. The last thing that you would do is actually get up from your desk, go down to the shop floor, gather your data, or go out into the field, or go into the classroom, whatever kind of work that you're doing. Gather your actual data, compute the value of your test statistic, and then draw your conclusions. So everything that we did today is done before you even gather the first piece of data. But then you have a simple criteria once all this desk work is done as to what values of your test statistic will cause you to accept the null hypothesis and what values of your test statistic will cause you to reject it. It's also worth noting here that this formula for our acceptance region looks a whole lot like our formula for confidence intervals. The only difference actually in the formula form is that our center of our acceptance region is now the value for mu that is put forth by the null hypothesis. So it's the value for the population mean that's claimed by the null hypothesis, whereas the equivalent interval for confidence intervals was centered on sample mean. So you've still got this z sub alpha over 2 sigma over root n expression for both confidence intervals where variance was known, and for these statistical tests of hypotheses, finding the acceptance region when variance is known. It makes sense because both of them are based off of the central limit theorem. So all of this work is being done under the, well, by using this fact that sample mean is approximately normal. So if we standardize sample mean, we get something that's approximately the standard normal. That is the core of all of the calculations that we're doing here, where we start thinking about these bell curves and left tails versus right tails. All of that hinges on the central limit theorem, and that's why we're getting some similar looking results here. That'll do it for today. So we'll briefly recap statistical tests of hypotheses next time. We'll do some more examples of what these tests look like. We'll do some full examples now that we've discussed the entire process. And then we will begin thinking about p-values also next lecture. And then I think our last lecture we should be able to spend some time talking about difference between means, test as to whether or not there's a difference between the means of two populations. That's a particularly important example because you might have a mean value for a control group and a mean value for an experimental group, and you're interested in whether or not the experimental group has had their mean value altered by whatever conditions are true for the experimental group that were not true for the control group. So hopefully we'll get to that in our last lecture. I thank you folks. Have a good rest of your day.